Hello. In this video, we're going to be solving question number 2 from the test number 1 remediation. Sorry. So first up, let's just read it. A massless inelastic string is attached to M1, 0.2 kilograms, slung over a massless frictionless pulley and attached to M2, 0.5 kilograms, in the arrangement shown. The coefficient of kinetic friction between all surfaces is 0.35. Determine the magnitude of the applied force needed to move M2 at a constant speed. All right, so let's look at this and ask ourselves, what are we trying to find even? The magnitude of force, okay, so we're looking for a force value, and needed to move M2 at a constant speed. Constant speed means acceleration equals 0, right? That would be useful. So first things first, let's define some of this stuff here. So we have M1, the mass of the first block, the little block there. We know that's equal to 0.2 kilograms, right? We also have M2. That's equal to 0.5 kilograms, right? Yes. We also have this coefficient of kinetic friction. Now, what does that mean? So, friction is a force that resists movement, pretty much, right? So when you push a box on the floor, there is a frictional force that is pushing the box the opposite way that you are pushing it. So let's say, here's your box, pushing it this way, friction, pushing it back that way, right? It's just fighting back, right? And there are two types of friction. There is kinetic and static. In this problem, we only have kinetic, so that's all I will talk about. Kinetic friction is basically when the object is already moving. Static friction is when the object is stationary, and that must be overcome. And once that is overcome, then kinetic friction is the force resisting the box, resisting the force. Sorry. Okay. So what is the friction coefficient? This is coefficient. Friction coefficient is usually represented by a mu, right? I'm going to write it like that. That's my mu, and that is equal to 0.35. Okay, so what is this mu? Now, mu is a ratio of friction over normal force. Now, what is a normal force? Normal force is a force that resists gravity, right? So if I'm pushing down on my table, right, what's stopping my fingers, my hands from going through my table? It's this normal force that resists gravity, right? You're sitting on a chair, I assume, right? Your body is being pushed down by gravity onto the chair, and a normal force is being pushed up, pushing you up so that you don't go flying down through the chair. Okay, now, let's talk about Newton's second law. Newton's second law is F equals ma. This A is acceleration, this m is mass, and this F is force. Now, there is a thing right here, right? That means sum of, right? So the sum of the forces equals mass times acceleration, right? Now, how do we know what our forces are? Well, let's see. In order to find our forces, we need to draw something called a free body diagram. And before we do that, let's identify what force is. Now, force is recorded in the unit newtons, and newtons are just a different way of writing kilogram meters per second squared. Now, why does this make sense? Well, it makes sense because if you look at mass is in kilograms, right? 0.2 kilograms here, 0.5 kilograms here, mass is in kilograms, right? Acceleration is in meters per second squared, right? And kilograms times meters per second squared, m times a, equals newtons, right? And that is our forces that we have here, right? So, but how do we find these forces and see how big they are, what's their magnitude, what direction they're acting in, yada, 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 right? So let's do that. let's draw what we call a free body diagram. So here is my free body diagram of mass 1, right? As you can see, if this was a diagram of it in the problem, there would be a string coming out here, a pulley, another mass underneath, but we don't have to draw all of that. This is just mass 1, M1. That's all this is. And we're going to draw the forces that are acting on M1. So the first force acting on M1 is gravity. Well, not the first force, but this is just a force that I'm going to put first. So this force acting on M1 is gravity, right? Force of gravity represented as M1g, right? Mass times acceleration due to gravity, right? So the force of gravity is equal to the mass of the block times acceleration. The acceleration due to gravity is g, and g is roughly equal to 9.81 meters per second squared, but we're going to keep it as g for as long as we can. Okay, now, obviously, we're going to have a normal force resisting this, right? Block isn't going down. Block is staying where it is in the y direction, up and down. I will define axes in a second here, right? So this is a normal force, our normal force of block 1, we'll call it, right? Now, we also have a force pulling this way, right? What is that force? We know on this that the block is moving that way because of the force applied, right? So that means the string will also be moving that way. And since it's moving that way, on this side, it will be moving that way. So the block will be being pulled that way by tension. Now, another thing we have to do here is there's another force here. And that is the force of friction between number 1 and number 2. In fact, it's the frictional force that 2 is putting on 1. Now, let's define our axes, right? For this block, we know that it's going to be moving to the right, right? So let's make that our positive x, right? So let's make this plus x and this plus y, right? So our x-axis positive to the right, up is our y-axis. Okay, good. Now, let's do that for mass 2, which is a little bit more complicated. M2. So, in M2, we have the mass of M2 going to the ground, but we also have the force of M1, and that's because M1 is on top of it, right? So we also have M1g going down as well. We can see it already here. We have the force applied going to the left. And on the back, we are going to have a tension force. And there are 2 more forces here, both of which are friction. Because this block is in between the ground and the first block, M1, there is a frictional force of each. So this frictional force on the bottom here, we can call F of gravity on block 2. And this frictional force between number 1 and number 2 is going to be friction of block 1 on block 2. And right now we haven't drawn any forces going up, right? There has to be a normal force resisting these 2 forces going down. And we will define our axes as this. This will be plus x, this will be plus y. Okay, now that we have these, let's put these into this formula here, our Newton's second law equation. And what we should do first is we need to break these up into x and y. Luckily for us, all of the forces are already aligned with the axes, meaning there's no force going diagonal like this where we have to break up into that force and that force. We just have straight forces aligned with the axes. So let's do that for mass 1 first, right? So the sum of the forces for mass 1 in the y direction is equal to our normal force is going up, so this is normal force, minus mg. We know that to be equal to 0 because it is not accelerating up or down in the y direction. It's staying still in the y direction. And we can rewrite this since we know it's equal to 0, these two must be equal. So N1 is equal to M1G. There should be a 1 here, right? So let's do that for the x direction. Sum of the forces of M1 in the x direction is equal to, going this way, tension is positive, tension minus friction of 2 on 1. Now, we do not know what this frictional force is, right? But we can rewrite it to a point where we can figure it out. So, like I said before, friction, or the coefficient of friction rather, is a ratio of friction over n, right? And we know n here. So if we multiply this n on both sides, we get the ratio, or not a ratio, we get, that's not a mu n equals frictional force. So let's rewrite this as tension minus mu n1, right? So now we know that to be equal to 0 because, like it says here, constant speed. So speed isn't changing, acceleration is constant. So we know that tension is equal to mu n1. We also know that this frictional force is equal to mu n1, and that is equal to tension. They're all equal to each other. Now, one very important thing is that this string, since it is inelastic, the tension is the same at all parts of the string, right? So the tension pulling here will be the same as the tension pulling on this part here. They will be, yes, forces of equal magnitude. That will be important later, okay? But first, let's do the same thing, except this time for mass 2. So let's write sum of the forces in the y direction equals mass times acceleration, which we know to be 0, right? It's not accelerating in the y direction. And that's equal to n2 minus, right? Because n2 is positive in our positive y direction here, going up, minus m2g minus m1g. Now we can write this here, factor out the g. We can write this as m2 plus m1 times g, right? Just simplifying it. Now we know that these two will be equal to each other since n2, if n2 minus this is 0, then they have to be equal, right? So we can rewrite this. n2 is equal to m2 plus m1 g, right? Yeah. Okay, now let's do the same thing except in the x direction. So the sum of the forces in the x direction are equal to the force applied minus, because the force applied here is positive x direction. So that means these are negative x direction. Oops. These will be negative x direction, so they will be minus tension, minus force of gravity on 2, minus force of 1 on 2. Now, we already know this tension, right? We already know the frictional force, right? Because if you look here, this is the frictional force of 2 on 1, right? So the frictional force of 1 on 2 will be the same magnitude, meaning it's the same size, just going the opposite direction, right? And you can see here it's going the opposite direction. So we know that to be true. So that means we just need to find this force, F of G, F of gravity, the frictional force of gravity on the second block. So how do we do that? Well, we know that, where's my mouse at? Here it is. Mu is equal to frictional force over normal force, right? So what we do here is we multiply this on both sides, this n, and we get mu n equals friction. Now it's important to realize what n this is. This is this n2, right? Because we're talking about the second block here. So n2. Now, how do we calculate n2? if we go back to our equation for the y direction, we have this equation here that N2 is equal to M2 plus M1 times G. Now, if we put that into a calculator, we can get M2, which is 0.5 plus 0.2 times 9.8 times 9.8 equals that, equals 6.86. And when we multiply that by our coefficient, right, because remember it's M2 times coefficient, time multiply that by 0.35, our frictional force equals 2.41. And this is frictional force ground on number 2. So we just have tension and this force left, right? So let's find those. So we know tension to be mu N1, right? So let's calculate that real quick. Mu times N1, right? So mu, 0.35, times N1, which is, if we look for this here, N1 equals M1G, so 0.35 times 0.2 times 9.8 equal to 0.686, right? Now, if we go back to this equation here, we know that the magnitude of this tension and this frictional force are the same. Because this acceleration is 0, remember here, we found that the frictional force, the magnitude of the frictional force is equal to the magnitude of the tension because the acceleration is 0. So we can plug these two numbers into this equation. So we have force applied minus tension minus force of gravity on number 2 minus, or not force of gravity, force of friction due to gravity on number 2 minus force of friction from block 1 on block 2 equals 0. We can make this equation equal this, F force applied equals tension plus force of gravity on 2 plus force of 1, or force of frictional force of 1 on 2 and frictional force of gravity on 2, equals, boom, what? We put this in the calculator. We know 0.68 are these two. These two are 0.68. So multiply 0.68 by 2. We calculated this value right here, 2.41 plus 2.41. That gives us a final answer of 3.78 newtons. So that is the minimum, or the only force, that is the force needed to move M2 at a constant speed at 0 acceleration. Thank you.